Hi, I'm Mr. Kangas, and today we're going to take a look at Chapter 7, Section 4, Constant Rate of Change and Direct Variation. Now, there are two real key concepts that we're trying to get across in this video. The first one is constant rate of change, something we may have discussed briefly before. And it's something that every linear equation has. Because all linear equations create straight lines. Okay? So what they represent is a constant rate of change between the x and y coordinates. So if you were to look at a table of a linear equation of x and y values, and you were to list off the x coordinates in such a way that they either are going, by 1s, 2s, 3s, 4s, whatever it may be, but the space between each x coordinate is the same. Because remember, I believe I've talked about this in previous videos, but if not, one thing you're going to notice about linear equations is literally all linear equations and all nonlinear equations touch every single x coordinate. So before I jump into this, you take a look at a coordinate plane. All right, the middle here is 0, and as you go to the right, all of the positive numbers exist, and as you go to the left, all of the negative numbers exist on the x-axis, okay, which is this horizontal line here. Now, all lines, curves, and waves move from left to right forever. They don't necessarily move up and down. Most linear equations do move up and down forever, but most if not all of the curves and waves do not move up and down forever and ever. There are certain examples of lines that do not go up and down forever, such as a horizontal line, which technically is a linear equation and that is not moving up and down forever. But one thing, all lines, curves, and waves, or in other words, all functions, one thing that is true about all of them is their x-coordinates move from left to right. Okay, the lines, curves, and waves all move from left to right forever and ever in both directions. So if you take a look at a line, let's draw a line here. Okay, this line is going forever to the right and forever to the left. So eventually this line is going to touch every single number on the x-axis and every single number on the y-axis. That is not always true for the y-coordinate, however. But it will always be true whether you're dealing with a linear or nonlinear function. It will always be true for the x-coordinates. So you can pick any of them you want, and as long as you're going up as long as you're equally spacing your x-coordinates apart, you're going to notice, if you're working with a linear equation, you should notice that there's a constant rate of change going on as x changes. Okay, so where x is changing by 1 in this instance. Okay, now let's say we were working with the linear equation, and I know we haven't had a whole lot of experience working with them yet, but we'll go with this one. Okay, this is a linear equation. We'll talk more about these in future videos, but basically all you do to find the y-coordinate is we've picked x-coordinates. Remember, all lines will touch every x-coordinate. That's why I can pick any number I want here for x. I input these numbers myself, the 1, 2, 3, and the 4, because the x in this equation represents the x-coordinates on my line, every x-coordinate. The y represents all the y-coordinates, and together the x and y represent ordered pairs. So when I plug in 1 into this equation, because I know 1 will work for this equation because every number works for x in this linear equation, because my line's going from left to right on the x-axis forever, so it's going to touch every single number. So I can plug in anything I want for x. So I'm plugging in 1. Okay? 3 times 1 is 3, plus 4 is 7. I'm going to plug in 2. 3 times 2 is 6, plus 4 is 10. I'm going to plug in 3. 3 times 3 is 9, plus 4 is 13. I'm going to plug in 4. 3 times 4 is 12, plus 4 is 16. So y equals 16 in that instance. And what you're going to notice is y is going up by the same number over and over. So this is what we call a constant rate of change. This is how you know you have a linear equation. Linear equations always have constant rates of change. Okay, there are other ways to identify linear equations, but we'll talk about those in future videos. A constant rate of change represents a straight line, because straight lines never deviate. They never change their path. They're going in the same direction at the same speed forever and ever. And so what that means is every time I increase my x value, my x coordinate, my y is increasing by 3. My y coordinate is increasing by 3. So if I increase my x coordinate by 1, then my y goes up by 3. Increase x by 1, y goes up by 3. Increase x by 1, y goes up by 3. That rate of change between x and y is constant. Okay? So stays the same. Now, in something like a curve or a wave, our direction is changing. Here in a wave, our direction is changing. We're going up, we're going down at different rates. Okay, so a wave, you might look at that. If we're talking about driving speed, this line would represent me driving at a constant speed. I might be going 55 miles an hour, for instance. So every 1 hour would represent 55 miles. Okay, so after 1 hour has passed, I've driven 55 miles. Another hour's passed, I've driven another 55 miles. Whereas over here on this wave, it looks like I'm progressively getting faster and faster and faster, and then I start to slow down more and more and more, and then I start getting faster again. Whereas with this straight line, it represents a constant rate of change. So the same thing is happening over and over and over again. Now the other, there are a couple different types of linear equations you're going to see. You're going to see your basic linear equation, but there's a special type of linear equation, and it's known as a proportional linear equation. And this is where direct variation comes into play a little bit. But proportional linear equations, we showed you before on the table, we had x's and y's, and I went, my y's were 7, 10, 13, and 16, and so I was going up 1, up 3, so I did have that constant rate of change. But this was not what you would call a proportional linear relationship. A proportional linear relationship is when your x and y coordinates create the same ratio. When you take the y over x, when you take the y coordinate and put it over the x coordinate, you create the same ratio. So for example, you may have, let's go with 3, 6, yeah, we'll do 3 and 6. 6, 12, 9, 18, and then we'll go 12, 24. So as you can see, if you take a look at this, there are two things about proportional linear equations that stick out. One, all proportional linear relationships go through the point 0, 0. Always. They will always go through the point 0, 0. The second thing you're going to notice is their ordered pairs. All these ordered pairs create the same fraction. If I put y over x, 6 over 3 is 2. 12 over 6 is 2. 18 over 9 is 2. 24 over 12 is 2. Before I showed you a linear equation, it looked something like this. Okay? Now, the difference between this linear equation and a proportional linear equation is you actually don't have this over here, this plus 4. This is known as your y-intercept in a linear equation. The y-intercept in a linear equation is where your line crosses the y-axis, and the y-axis is that line right there in the middle. And so if this is 0, or if you don't see it, a lot of times instead of putting plus 0, you just won't see it. Okay, then that means that your line crosses the y-axis at 0. Which means your line is going right through the origin. Okay? And this is known as direct variation. And in direct variation, it's one, it represents a proportional linear relationship, but what it's telling, but it's a little bit easier to read, where this is literally telling you that y is always 3 times as big as x. Or you might have a 2 here, and so it's telling you that y is always 2 times as big as x. So that ratio between x and y is going to be pretty easy to see and understand. Y is always going to be half as big as x. Y is always going to be 5 times as big as x. But once you start adding in, y is twice as big as x plus 4, that's when the ratios created here start to get a little bit more skewed. So with a proportional linear relationship, your line is always going through the origin, and your line, the ordered pairs created by your line. So when you plug in numbers for x and you get answers for y, all of them will create equivalent ratios. So 6 over 3 is the same thing as 12 over 6, which is the same thing as 18 over 9, which is the same thing as 24 over 12. And something else, and this is going to be really important for you to write down, something else to take note of when it comes to proportional linear relationships is that the ratio created by your, the ratio that's created by your coordinates is actually the slope of your line. And I know we haven't talked much about slope, but slope is actually another way of saying rate of change, and we did talk about that a little bit. So slope is actually represented by every single ordered pair. Now this only occurs when you have proportional linear relationships, or in other words, a direct variation. So y equals 2x, y equals 3x, y equals 10x, y equals 1/2 x, something like that. You won't have a plus anything over here. Now, we did talk about a way to find rate of change using 2 ordered pairs. So why is it so essential that you have to go through the origin in order for direct variation to exist, or in order to have a proportional linear relationship? Okay, and to answer that question, it all centers around what we taught you about how to find rate of change using 2 ordered pairs, or 2 points on a line. We talked about how you do y1 minus y2 over x1 minus x2. Okay? Now, if you go through the origin, okay, and so one of the points on your line is 0, 0, right? Then at that point, when you go to pick your 2 points to find the slope, you can always, always, always use 0, 0 as one of those points. So I'm going to replace my y2 and x2 with point 0, 0. And now, since this is legitimately one of the points on my line, anything I plug in here for y1 and x1, any ordered pair, any point I plug in for y1, x1 will become the slope for my line, or the rate of change of my line. Okay? So this is really, really important to understand. But that's why that works the way it does. Now, if you don't go through 0, 0, you can't be proportional, because the only way for every single point to represent the slope, or to represent the same ratio, is to use this 0, 0. The second I put anything but 0, 0 here, the numbers I put on the left side aren't going to, when I go to subtract, I'm not going to get the same thing over and over again. I'm not going to, my coordinates, okay, my ordered pairs aren't going to represent my slope, or the same ratio, or my rate of change. Because the second I put something other than 0, 0 over here, that automatically means that anything I put over here is going to change. So if I put 1 and 1 over here, these are going to change by -1. If I put 2 and 3 over here, this will change by -2, and this will change by -3. So you won't get, basically once you put 0, 0 over here, you get y1 over x1. But the second 0, 0 is not there, this no longer works. And so you no longer have a proportional linear relationship where every ordered pair represents the slope. I hope that makes sense. If you have any questions, let me know. Make sure you pause the video and take notes. Make sure you pause the video and ask questions if you have them. Tune in for the next video. That's going to be on Chapter 7, Section 5.